Hi again, this is Mike, the Philosopher Engineer. Today we're going to talk about the value of reliability models. Now this week we've been focused on our knowledge base, how to develop it, how to manage it, how to apply it, and part of that knowledge base is our virtual models. So we talk about virtual models. Now I want to take that to reliability models. So the virtual model, similar to CAD, is our computer programs that represent our product. With CAD, we design things and we make changes, and we have configuration management. We're pretty careful about how we make those changes for each iteration and each revision. We want to have design controls and not get confused. Well, the rest of our engineering process should have the same type of controls. When we're when we're testing something, we also want to have a test protocol, and we have revisions on those. We want to get the data, and we want to make a report and capture all that work. And in the virtual models, we want to do the same thing. That's not always done. It's often done a little bit more informally, but if we invest more into those analytical models that look at function, we can really accelerate the programs. We can reduce the guessing, have a lot less trial and error. The trial and error mindset tends to cause a lot of delays that we don't really want. We're still going to learn from iterations, but we don't have to just guess. We can calculate and have a good engineering basis for what's going to happen, and then we go to the lab and test our prototypes. That's fine. So we have these iterations. We want to get the most value out of those things. We want to have the proactive work to understand what we're doing and why we're doing it. And then we can do what if scenarios virtually much faster. But now I want to take you to reliability models. And this topic is focused not just on the engineering side, but the management side, because all this work really comes down to a financial question. What is the investment? What's the value of that investment? Does it have a good return on investment? Everything really comes down to return on investment. Now, if you can develop your products 20 or 30% faster, that's probably kind of obvious. That's a great return on investment, but it really comes down to dollars as well. Afterwards, once we have these virtual tools, the virtual simulation tools help us understand the relationship between variability and function. And so we can do a lot of experiments virtually much faster. And then of course we'd still build them. It's not instead of testing. So it's not one or the other. I'm kind of always railing against binary thinking where it's either this or that, the extremes. No, it's really a balancing act. And where I see the opportunity as technology gets better, as computing power gets stronger, and these tools are really quite amazing, is we should really be increasing that ratio on the simulations and the models so we can go faster on our product development. And also that creates part of our knowledge base that we can do optimization, we do problem solving much more efficiently. Even with products out in the field, we should carry this all the way through the product life cycle, just like we do with the CAD. I mean, you don't get rid of the CAD when you launch the product. You may make some changes even after the product's launched and have future iterations. So what I'm proposing here is that we really use virtual models and then reliability models. But now let me go in a little bit more detail on what are reliability models, because I'm not sure everybody understands that. A lot of companies have reliability testing programs where they take so many prototypes and they test them and they look at the reliability. But testing doesn't create reliability, it just checks the reliability. What we can do with these virtual models is we can find what the reliability is at and then optimize it and improve it. And we can go through an ongoing improvement of reliability and have a predictive model. So in the reliability, the core element of the reliability is first you understand function, then you take each of these functions to the point of failure. That way you understand the failure modes and you understand design margin. Design margin is the biggest lever in reliability. Where does it fail and how close is that to the normal operating range? And you can decide if you need to change the design or add extra controls in your process, however you do that. Reliability we think of in terms of the product for the customer. When they take it out of the box, does it work the way it's supposed to? Is it broken? Is there a function that doesn't work? And then, there's the bathtub curve, which means that there may be some parts of the product that could wear out over time, like in a car. So you have sort of the wear and tear issues when you've used a product for a long time. But really the biggest thing is to make sure it starts out reliable and from day one all those functions are there. And in addition to having a reliable product, you don't want to have a low yield. So you don't want to get a reliable product just by throwing away 20% of your product. So that would be a yield problem, and that's really another loss on the financial side. So the reliability model involves breaking things. So you break them virtually very quickly. You can do a finite element model, you can do a math model, MATLAB, Abacus, ANSYS. There's all these different programs that we can use on our laptop to take our design and test it and then bring it to failure. And by understanding those failures, we can understand the basis of reliability. And we go to the lab and physically test and physically break it. We'll compare the two and refine and iterate. So those are good iterations. You make a lot of value out of it. Now, reliability eventually gets to the point where you understand the failure modes, and then you go into probability. And for probability, we almost always use Monte Carlo simulations. So your reliability can kind of go with the whole product lifestyle. You can cycle. You can have reliability numbers before you've launched your first product, and as you start building parts and your device or your product, you can get data that is more representative of the real parts, and then you can update those models. So Monte Carlo simulations are the standard statistical tool. It's really based on gambling from the Monte Carlo casinos where it came from, but the computer randomly throws in values based on the distribution, and from that you can find combinations that cause the most problem and quickly solve those. So we've done that with quite a few clients. It's really a great thing. So that's how they're done, right? So what are they? The reliability models are having a functional model, not just the geometry, but all the function, knowing where it fails, being able to break it virtually, and then from that look at the combinations that cause failure and then bring it into statistics. So the last part on top of that virtual model is Monte Carlo simulations. And we could do those all the time. And essentially we're doing testing on the computer. We can do hundreds of thousands of iterations with a Monte Carlo simulation while we're doing dozens in physical testing. And that saves a lot of time, a lot of money. It's a great investment. Probably I see typically about 3 times as much work being done on testing that I do on the simulations. I think that can be changed to your benefit. You can double the simulation budget and the effort in that area, and it will reduce the time and cost of testing. And so I think that's kind of the budget question and a planning question, and it's certainly something we can explain. Well, what is the benefit? I think I've already answered that. The most important benefit is you're going to develop the product faster, you're going to have more confidence in it, you're not waiting for failure to happen, you're going to be able to launch a product based on really the knowledge base that you know how this thing works and how it fails. And you have tools even longer term for optimization. Parts of your product may have small margin and you have to watch those carefully, and maybe 80% of the functions have too much margin. So it's overbuilt and overdesigned. Guess what? Those 80% of the overdesigned elements of your product are opportunities for cost reduction, opportunities for optimization. You can't really do optimization without understanding the mathematical relationship. And I'll leave it with one last thing, because you design a product, but it's only as good as your ability to manufacture it. So you're designing something and you're going to manufacture it. And there's variability in the parts and all the processes. And there's often a tug of war, I say a tug of war between performance of the product and process. And the manufacturer wants to have a wider window to operate, and from a performance standpoint, we want a smaller window. Well, how do we come to that compromise? How do we negotiate? What's the sweet spot where it still is reliable, but where it's reasonable to manufacture? Well, that's where math comes in. So once you set up these relationships, you have that sort of tug of war between process and performance, but you're making those decisions in an objective, quantified way with data, and then everyone is on the same page looking at that same data to make those decisions. So your decision-making process is a lot more efficient, it's a lot more objective, and at the end of the day, you're not gambling with your product and your customers, because that's why we do all this, is to make our customers happy with a great product. And we want it to be producible, we want great yields, and that's where the profits come. And that's how you have really successful companies, and it's fun when that happens. Well, that's all I have for right now, the reliability models. This is a big topic, we could go into it some more, but it's really proactive reliability. So I call that PAR. So you have your PAR model, proactive reliability. And that is, you're understanding reliability ahead of time. You have a tool you can continue to optimize and refine. And you can use these tools even after production to continue to improve your reliability through optimization. Well, that was quite a bit. but I think you'll be really happy if you really consider these tools. It can make all the difference in the world. I mean, give me a call, we can talk about it, but this is something I've worked with several clients to really go down this path and into all the simulation models, what we call code really, and then we refine those virtually much faster, and then we build a Monte Carlo analysis for the reliability. It's fantastic. I've really enjoyed it, and the customers have a lot more, or our clients have a lot more confidence in the development of their products. All right, well, hope you're all safe and doing well, and have a great day. And I enjoy these conversations. Please share any notes and subscribe to my YouTube channel if you could. I know I normally share these on LinkedIn, so not too many people go to the YouTube channel, but it's organized in a way where it's a little bit more accessible. So all the same types of videos go together. And there's even a module there for March Madness, which kind of covers the whole process. So have a wonderful day. Thank you very much. Bye.